Good evening. Thank you for coming. Before we get started over here, this is one of those important things that have happened in the last couple of days. I don't even think this has been announced yet, except on the web there. We have at least one comet, maybe two, that we need for April of this year. The first one's Comet 2026 A1, or nicknamed MAX, for people that went did the observational work in the southern hemisphere. It's a possible early April object. The object itself, the comet head, the nucleus, is about 1.5 miles across, which is about average, maybe a little bigger than normal you would have. It was discovered on January 13th of this year. It's going to pass within 500,000 miles of the surface of the sun, which means it might be able to survive. And if that happens, it's going to be, could be a terrific evening object, visible right out here. That telescope, binoculars make it look really great. It works out. For those that are into more technical stuff, it's part of the Crux family of comets, which are sun grazers. They come sometimes perilously close to the surface of the sun and usually burn up. Now, if we're lucky, one of the two of these might survive and come out, and like I said, the first one over there comes in about 500,000 miles from Earth, which means we should have some real picturesque view of the evening sky in the west. The last good comet, by the way, at least naked eye for the general public, was Comet Hale-Bopp back in 1994. It was discovered on July 23rd. The formal name is Hale-Bopp, named for two people, Hale and Bob. One a professional, the other an amateur astronomer. C 1995-01. And then just as I came down here, I went on the computers, and sure enough, another comet's going to be coming in. Pan-STARRS C 2025 R3. Its perihelion, its closest approach to the sun, is April 20th, so we may have another pair of comets coming in, so stay tuned. If we can see it from here, we'll make sure you can see it as well, even if we got to use the parking lot across here to look to the west. Unless somebody's got a chainsaw about 20 minutes. You can get the trees down here, which I wouldn't want to do, by the way, but it's a great idea. So right now on orbit, actually a very distant orbit, it turns out, from the Earth, is a very large telescope. It is the largest space telescope yet put on orbit, at least on orbit within the Earth-Moon system. It is big, as they say. It's 6 meters across, which is huge compared to any telescope that's ever been up in orbit. So we're going to talk about the building of it and a few of the discoveries that were made with it to date. So let's move on. Okay. After about 30 years of development, the largest telescope ever built for space astronomy. It's been constructed, tested, launched into space, and is right now in the middle of a 10-year mission. It's viewing the entire sky that is visible to it. We will discuss the design, testing, calibration, and ongoing mission of the James Webb Space Telescope. Next, please. Okay, just a thought. It's necessary to prepare quite a perfect telescope, which will show all objects bright, distinct, and free from all haziness. That's Galileo. In his book, which for many, many years was banned by the Catholic Church, it's been rehabilitated after a lot of evidence showed that, gee, the universe is magnificent. And there we are. Sidereus Nuncius, or the starry messenger, in 1610. Next. Okay, well, first things first, the telescope was named for someone, obviously. So this is the gentleman, James Edwin Webb, was an American public servant and a second administrator of the National Aeronautics and Space Administration, NASA, during the Apollo program, 1961 to 68. He strived to find a balance between science and the goals of human spaceflight. Next. Okay. So some objectives that investigations of James Webb will do. What did the early universe look like? When did the first stars and galaxies emerge? How did the first galaxies evolve over time? What can we learn about dark matter and dark energy, which is a big controversy nowadays? How and where do stars form? How do stars die? And how does their death impact the surrounding interstellar medium, the surrounding space around a given star. And that can go very, very far out. Where and how do planetary systems form and evolve? We are in a planetary system. There are many, many of them scattered throughout the Milky Way. And if you understand how other systems operate, you can understand what's going to happen here. So there's a direct connection, a lot of these things, to the everyday life of humans here on Earth. Next. Okay, so why a space telescope? Believe me, if I had the money that went into the James Webb, and we had only had to put together a big observatory, I think a monster telescope, something like maybe about 50 or 100 meters across. That's a huge piece of equipment, and it can be done. However, our atmosphere is wonderful and terrible. It's wonderful, we can breathe. It takes us a little time to get a sunburn from the sun, so ultraviolet light does get through. It also traps heat from the sun, so our planet is a big ice ball. But it does other things too. It blocks out radiation that we need to study to understand the universe around us. Gamma rays, X-rays, and ultraviolet. We get a little touch of ultraviolet light when we get sunburned, for example, or tan. We are insulated from that end of the spectrum for the most part. Visible light, observable from Earth, with some atmospheric distortion, some, yeah, I would say so. Most of the infrared heat is absorbed by atmospheric gases, best observed from space. Radio waves that can be observed from the Earth, we can do some. And long wave wavelengths, though, radio waves are blocked. So going into space is necessary to really get the full picture of the universe around us. Next, please. Okay. Just to give a comparison, what sees where. The Hubble Space Telescope has a range of 90 to 2,500 nanometers. In other words, from the near ultraviolet into this through visible into the infrared. The James Webb Telescope sees mostly in the infrared. It starts in the visible red and extends out to about 28,500 nanometers. These wavelengths, in particular with James Webb, are important for understanding how stars form, how planets form, how galaxies have been evolving and changing over many, many billions of years. There's another instrument, but a much smaller one, that actually, well, I'll say it like it is, it ran out of coolants to keep it cold enough to be able to look at the far infrared, the Spitzer Space Telescope. It's a shame, too, it's doing a lot of really good work, but unfortunately, it had one big defect, or call it that. It used liquid helium to cool its detectors down from about 3 to 4 degrees above absolute zero. That's roughly about 445 degrees minus zero in Fahrenheit. That way, its sensors are made very, very sensitive, so they can see faint objects, including even planets as they're forming. They're warm, but they're not hot enough to shine of their own light like a star might. So this is the big reason why we need this section, from just starting in the visible all the way out to the mid-infrared. Next. Okay, give comparisons number 2. The primary mirror of the Hubble Space Telescope is about 2.4 meters across. The James Webb is 6.5 meters. And notice, it's not one mirror. It's a number of mirrors that are combined together. Also, a Hubble Space Telescope uses aluminum and ultraviolet coatings to be able to see the sky. The James Webb uses two very exotic materials. First of all, it is using gold to reflect the infrared. Gold is almost 100% reflectivity in red all the way through the infrared. It also is a space material which has to survive relatively cold compared to the Hubble Space Telescopes. Hubble Space Telescopes are a little bit around the Earth. The James Webb Telescope is in a point in space where the gravity of the Earth, the Sun, and itself balances. And that way it can stay in one place and be viewed for hours on end. Its mirrors are not made of quartz. Its mirrors are actually made of a material called beryllium, which has in space is a zero expansion material. It also is very difficult to operate when you're trying to polish it here on Earth because beryllium, some of you may already be aware of this, is highly toxic. So they had to put a coating over it. The coating that they chose was gold, which reflects very high into the infrared. Next. Next. So this is just a general overview. Primary mirror is 18 hexagonal segments made of beryllium coated with gold. Secondary mirror reflects gathered light from the primary mirror segments into the science instruments. On the other side of the telescope is the science instrument module, which has all the cameras and scientific instruments. And to stabilize the vehicle, just in case, it has a trim flap that allows the light of the sun actually to move it just a little bit incrementally, just enough to hold it in place. It has a solar power array, which is always pointing toward the sun. Earth pointing antennas comes in handy when you want to communicate with them, of course. And a spacecraft bus, which has most of the steering and control mechanisms within the telescope. And star trackers, which are nothing more than small telescopes that keep the instrument once it's on a target. It looks for stars nearby and locks onto them. Okay. Next, please. Okay. So we could have done this by ourselves, but it's better to work with other people. They get better ideas, perhaps collectively. The science instruments were built by a European Space Agency and NASA. The near-infrared camera, farthest objects ever seen in the near-infrared, was NASA's work. And then the Canadian Space Agency helped us making the near-infrared imager and slit spectrograph, essentially NIRIS, allows us to not just look at an object, but to analyze the light coming from it, tell us what it's made of, its temperature, distance, a number of things all at once. Or to put it another way, a good part of the world is participating in this adventure that we call the Space Telescope. Next. Okay, Canada in particular, I'd like to go with on this because they did create the near-infrared imager and slit spectrograph. In other words, it's an instrument that breaks down light, tells us temperatures, distances, velocities that are coming toward us and away, even its age and how it's evolving over time. And quite frankly, a lot of money went into building the telescope, but not all the instruments, and Canada stepped forward. So our friends to the north really put in the lion's share of sensing what's in the universe with us. It's terrific. NIRIS will tell us the age and distance of galaxies, the size and their shape, and the stage of evolution. Believe it or not, galaxies are born, they evolve, they change, very much like human beings, and eventually they may die. Or at least they become, from a scientific point of view, no longer active. So reading that tells us how the universe is changing and what may happen in the future for us. Next. It is an overview of the structure. There's a fixed, there's a secondary mirror and a tertiary mirror. The primary is actually made up of 18 of these segments. Again, they have controls to allow all these mirrors to come together and align properly so you can put in imaging with the telescope. Thermal management subsystem is very critical to keep the electronics active because without that kind of control, they probably burn out just from the sheer heat of the sun that they can't throw away by themselves. In this case, it cools them down. The optical design, a little bit of optical gobbledygook, so bear with me for a moment. The James Webb Space Telescope is a 3-mirror and astigmat featuring an ellipsoidal concave primary, hyperboloidal, that's a killer of it, a convex secondary, and ellipsoidal concave tertiary. Or to put it another way, if you have astigmatism, you wear glasses to correct it. If you're just nearsighted or farsighted without astigmatism, you need eyeglasses to correct that too, different types of lenses. And the convex secondary amplifies the focal length. And our telescopes, we call it a Barlow lens. But in this case, it's all done part of expression. It's all done with mirrors. Or to put it another way, it allows correction of coma, off-axis astigmatism, and spherical aberration, but with a wide field of view. To put it another way, if this was a camera lens, you'd be able to photograph anything at all here on Earth and in the sky if it was just a camera lens, and that's exactly what this instrument is. It's a giant camera on orbit near the Earth. We'll talk about where near the Earth in a moment or two. Next. Okay. Ready to take on the mirrors. This is the truss that holds all the separate 18 segments that make up this gigantic mirror. By the way, 6.5 meters is a little bigger than from the front here to that rear door. It goes a little beyond that. So that's a big mirror. Mirrors. First of 18, they have a special device to put it gently and firmly into one of a number of cells. See here. Next. And there they are, all installed. Yes, there's the gold coating. This will allow it to be able to reflect in the infrared. And if I remember correctly, the wavelengths that James Webb operates, gold is almost 100%, like 99.9995% reflectivity. Now that almost no photons get away from our detectors. Next. Each mirror cell is separate. The mirrors themselves, the substrate stand facing down in this case. You can see that it's all little braces all through this. Beryllium is the lightest substance on the chemical chart, temperature periodic chart. Unfortunately, it's also quite poisonous. So the opticians had to do very, very difficult work on a material that just flat out was not like to polish very well. To get all 18 segments together without losing a single one. And to allow it to be lined up, all the mirrors to line as one giant mirror, they have actuators, special design of what they call linear motors that allow it to be tilted and tipped properly to hold them all together. Next. Okay, so there we are, getting it all together. And I know that we were not going to make this big fairing, almost about 18, 19 feet in diameter, to put it on top of a rocket. No rocket had ever taken. So we had to fold it all up. And yes, Northrop Grumman did quite a bit of this work. So there are the secondary and counter systems back here. The first of the three segments of segments are all folded together. Then this section here, which is a gigantic heat shield, to keep the heat of the sun from affecting the telescopes and the cameras. So this all had to be packed together to fit into the rocket fairing. So a new selfie. Everybody's got to take a picture. And there it is. Now you can see the gold coating. So as well. And one guy shy is over in the back there. There are 4 people over here. My hat goes off to these guys and girls because, quite frankly, they had to work with a rather poisonous material. They had to make sure everything was set up. We learned from the Hubble Space Telescope problems that do occur when there's no communications. But here, everybody was talking together, and they had consultants that were on throughout all. Next. The primary mirror, as it would be was assembled, all set to go. Next. This is the crew, part 1. These are the people that helped assemble this. They're all in clean room environment clothing. There's the folded up mirror system. This will eventually be folded up as well, so that the heat shielding will all fit into one, more or less, even cam. Next. And then the mirror placement. I show this just to show the work that had to be done. All these had to work. I admit personally in my optical career, I've never worked beryllium. As a matter of fact, I talked them out of it because how dangerous is beryllium? Beryllium is name means sweet in Greek. Unfortunately, though, it's also quite poisonous. And the way you know you've been poisoned, you should get this wonderful honey taste now. Now, I've never had it, but I talked to people that did it. One guy was at a hospital for 3 weeks, just getting over it. Stuff was incredibly toxic, and they didn't lose anybody. I have not even heard of anyone being sickened by it, so that's pretty good. And I point out this mirror here, C3. C3 has the dubious distinction that when it's on orbit and was going through its certification to make sure everything was working and such, it took a hit. There was a micrometeoroid, couldn't be more than maybe, I don't know, about a 64th of an inch, but something impacted it. And we know that because all these mirrors have to be aligned with special actuators. That one particular mirror suddenly was out almost to the point that they couldn't use the mirror. They managed to do some things on the ground and they got it to align, but we know that there's a hit of something there, probably, I'd say maybe the eighth of an inch. All that work, some little baby space rock comes out and tries to hit it. I'll tell you, nobody appreciates opticians. Next. And this is an all-up test. This is the world's largest vacuum chamber for testing of components to go into space. And went through flying colors. This allows you to be able to heat up or cool down a vehicle and see its reaction. It turned out perfectly well. Next. Now the mirrors themselves, before they were transported out, they had to be covered up to make sure no dust got on them. You wouldn't want to have the thing shipped out in its final stages and then have dust everywhere, and it does occur. Yes. Keeping cool, these are Mylar blankets. There's about 6 of them, if I remember correctly. These are about half the size of a football field. Just keep the heat of the sun away from the optics. Well, put it this way, if it overheated like that, there'd be no more telescope. Sensors take the place of film that we'd say use here on Earth. Even today, they're getting away from film. I guess everybody knows the digital cameras. Next. Okay, so here's the crew, all the administrators and the opticians and everybody else that worked on this. It's a whole scale model. See how big James Webb is. Quite a beautiful piece of equipment. And this is on orbit right now in operation. Next. And you have to fit the fairing over it, so you don't just put it on top of the rocket. It's got to be shielded from the atmosphere as it goes through. Because remember, this is going to have to go almost.
If you have up just a little bit louder.
A bit louder?
Yeah, thank
you. A little bit? I'm sorry. You know, speak softly, make it tell so. Okay. They fit the fairing over the collapsed telescope because as you're moving through the atmosphere, you're going faster and faster. This is designed to operate beyond the Earth-Moon system. It's behind the moon, and it has to be where it is extremely cold. And this fairing kept it isolated from the atmosphere of Earth as it was soaring through it. Next. And it's ready to go. The Ariane rocket launch was launched in so the European Space Agency was with us. We had a lot of people. That's one of the great things about space exploration, ladies and gentlemen. Everybody puts away, for a moment, puts away all our politics, puts away our belonging, are yelling at each other and the whole thing. They work for a common goal. In this case, trying to understand the universe around us. Now, we do that kind of cooperation, we would have some baloney going on in our country and the rest of the planet. A little pontificated in there, but I think that it's true. Exploration tests the best of us. This is one of the best pieces. Next. Ignition and a liftoff. What a Christmas present. There we go. And she performed beautifully too. Okay, next. And last look, this is the last image that we got from a camera in that fairing, looking at the soon-to-be deployed James Webb Space Telescope. That's the Earth beyond it. And this little thin, almost purple blue line, that's how thin our atmosphere is. It's 10 miles of air. And that's what keeps us alive when we live down to. So it's a hail and farewell to this. Next. The path to its station, essentially what's happening, what had happened, they had various times that had to be done, the fairing had to separate on time, had the entire thing had to be separated from the launch vehicle. Solar array had to be deployed. That's one of the most important parts at this point. Because without power, the batteries have no way of recharging themselves. Luckily, everything's working like clockwork. A day later, the gimbal antenna assembly or communication system deployed. The sun shield started to be deployed over a period of days. Then the primary mirror segment assembly was deployed, along with, it turned out, and wing deployments. Those wing deployments they refer to as solar panels, so they could power up the vehicle. Launch plus 14 days, the secondary mirror assembly was deployed, and it is actually orbiting around a point in space called L2. It's a good place, by the way, to put space stations, too, if you want to get out there and do experimentation, because it balances the Earth, the Sun, and whatever's placed here almost perfectly. Basically, is what they call a halo orbit. There is a mathematical point here, essentially circling around it. It works beautifully. Next. So there's the trip out to L2, Lagrange point. And to the second point, it's about 1.5 million kilometers from Earth in the direction away from the sun. You can always block out the sun and light and heat from the sun and Earth with a sun shield to be able to observe the universe in the infrared. It's not a fixed point, but it follows the Earth around. It's a nice place of gravitational balance. Okay, so setting up a business, you can see boys, initial sun screen, tensioning and separation of the layers. The secondary mirror support is unfolding. I mean, this is the biggest origami puzzle that's ever been created to date. And it worked fine, absolutely perfect. Yes. According to the telescope now, the Space Telescope Science Group sends commands to Webb and receives its data. Basically, commands come from the Deep Space Network up to the spacecraft, communicates down with information, and that data is then transferred to the Space Telescope Science Institute over here in Baltimore, Maryland. So the universe follows Baltimore. So this is what's all on board. MIRI, and we'll have this the alphabet assemblies in a few minutes. Mid-infrared instrument looking for cold, distant objects in the mid-infrared. And it's got an extra refrigerator. It brings it down to minus 266 degrees centigrade. That's about 405, I believe, degrees Fahrenheit. So that'll freeze things down and allow our sensors to be able to be sensitive enough to be able to see in the infrared. Near-infrared spectrograph or NIRSPEC, temperature, mass, composition of objects, mapping and spectroscopy, so you can see how much hydrogen is in the area, how much of lithium is over here, how much of any other element or anything else. And it can capture spectra, how we analyze light. Of 200 objects in one shot. Not bad. The near-infrared camera, NIRCam, farthest objects ever imaged in this wavelength of light, the near-infrared. It's a critical role in telescope alignment, too, because everything has to come together for those sensors. If they miss, you can still do the work, but you're not getting as much light as you should be getting. Light from the first stars and galaxies, gathered by the the near-infrared imager and slitless spectrograph. Essentially, it breaks down light into its component colors, and spectra allows us to find out composition, temperatures, distances, pressures. All this. We can look for molecules in exoplanet atmospheres. Yes, we can just about image nearby stars just well enough be able to determine the composition of its atmosphere, temperatures, maybe even the chemicals of life. And it's high precision pointing, as you might expect. Next. So this is a quick overview. This is how we have before this telescope origami, how it deploys its way out, the sunscreen comes out, then the instrument itself. This is an overview of the instrument. The primary mirror made up of 18 mirrors. Science instruments are behind it, accessible to the secondary through the hole in the middle, just like our 24-inch telescope over here, classic. Unlike Hubble, it is composed of several mirrors, 18 mirrors total, but they work together. This is the Hubble mirror, 2.4 inch, with 2.4 meters across. This is 6.5, and is a 6-foot human, just to give an idea of how big this really is. And they all work together, and they can aim accurately, less than an arc second for each mirror relative to everybody else. And it has to be kept cool, because remember, you're still close to the sun. So the cooling system, sun shield, basically this layered mylar and other materials keep everything cool, almost to the point of the temperature of space itself. And then the rest of the way it's taken down with what we call Peltier coolers. Okay, next. So here's the overview of the instrument. It has 4 science instruments. The NIRCam, a wide field near infrared camera covering wavelengths from the orange, actually, all the way to 5 micron in the infrared. NIRSpec, a wide field view, multi-object near infrared spectrum. This we want to look, for example, at stars nearby them to see if there are planets, maybe get an idea of the temperatures and pressures there. MIRI, I like this instrument, combined mid-infrared camera and spectrograph. You don't just look at the object, get a picture of it, but you can analyze chemically what you're seeing. And the FGS MIRI's, a combined observatory fine guidance system you need to be able to lock on an object, and the near-infrared imager and subtle spectrograph. Wavelengths again from about 600, actually it's about 600 nanometers to 5 micrometers. Has a 2.2 by 2.2 minute field of view, very tiny, that allows us to look specifically at objects and be able to analyze them individually instead of a whole field of view. The European Space Agency, NASA, and the Canadian Space Agency have collaborated since 1996 on the definition of the successor to the Hubble Space Telescope. Well, I'm of the mindset that when you got a working telescope, you don't just put it out for pasture. So Hubble is still operational. It's still got, miraculously, it still has funding. There's things it can do that James Webb cannot. Different wavelengths. So put them all together, you get everything. We hope. Next. And there's packages, NIRSpec spectrometer, NIRCam over here, faint object spectrograph, and MIRI, almost out of the picture. The optical bench, these are all not just in boxes, set up precisely so that all the optics and mechanical stuff work together. Spectrometer on the top there for 3 optics. The main optics just below it. Or to put it another way, this is an analysis system. You can look at the light of stars, of galaxies, planets, and be able to see the composition in exquisite detail, and if there are any changes, be able to document it and interpret what that is. This is the actual instrument itself. Next. Methods of observation, number of them. Wide field without slits, in other words, visual photograph. Single object without having a slit to restrict the field of view. And of course, you guessed it, some of it has to be slitted, so if you look at just one particular object. Multi-object capability, a field unit that allows us to look at various parts of a given area of view. And a time series to see if there's any change in a given object over periods of time. There are some stars that, as you may have heard, that are variable. Their light output changes. Even the composition sometimes changes. This is one way of being able to see if a given object is doing this or not, and maybe why and why not. Next. So this is what the James Webb can see in wavelengths in the infrared all the way out almost to 28 microns wavelength. The various instruments. This is really the wide expression. The hot spot, the infrared, the near infrared, it reveals, for example, planets, comets, asteroids, dust that's formed by starlight, protoplanetary disks, where planets are forming even as we watch. Visible, this is the light we see, I guess to the James Webb, it's sort of a little boring. But near infrared shows polar red stars. The dust is in between stars is transparent. So it allows us to see what's hiding in places that stars are forming. Next. This is MURI camera. It's got spectrographs, various wavelengths. This is where it usually is viewing. The field of view is quite large, mid-infrared. There's a coronagraph. If you block out a star, like we have an eclipse here on Earth with the moon getting in the way of the sun, look past it, maybe discover other planets, information. The integral field unit basically pulls all these together so that you look at an object, such as in this case, you look from a galaxy, you'll be able to close in on the area and know what you're looking at. And I think it's almost a self-guiding system. Next. Here's the MURI imager. It's 18 station filter wheel, 10 filters, very specialized prism, chronographic diaphragms that allow us to be able to dial them in effect. I don't want to look this big freaking area. I want to look at this big style. You can open it and close the lens. Focal plane module, as it's called, it's operating at 6.7 degrees Kelvin. Or to put it another way, roughly 410 degrees below zero Fahrenheit. We need that so that we can see objects in the infrared because they're putting out heat. Probably like looking at a candle flame, maybe a half a light year away, and it can do it. It's the optical design, just the focal plane to the detector of the instrument, of the telescope rather, and then the optical camp again, picking up light for analysis. It's quite an amazing piece of equipment. I'm not going to really go into super detail. Suffice to say, this allows us to look at the mid-infrared, see planets forming, stars dying. What is happening with certain galaxies? How are they coming together? Why aren't they in certain cases? It gives us a picture of the universe that we never have had before, any kind of great detail like this. Next. Okay, NURCam. So a little more complicated. I'm not going to go completely through all this, but this instrument allows us to be able to look at objects close to each other in a cluster. The star. Where'd that nebula come from? Okay, good. Got that. Back and forth. All through this instrument. And they have mirrors all through. I love this because I used to be a senior optician in an optical company. And be able to see the path of the light and such and how it's going to work. I get very enthusiastic about it. This is really terrific because it allows you to be able to pick off the light, be able to sense it, and again, get this information. This way we have more knowledge of our universe around us. And this is all mechanical stuff. 10 years ago, this was unheard of. Now it's up there. And it's doing its job. Next. Near infrared spectrometer. I'm not going to go completely into this, but you can see where it will pick off light from a given object, bring it through instruments and detectors, which allow it to be able to see in the near and far infrared and some visible so that you're able to guide on the object. It's quite complicated. I'm not going to go crazy about it. I can go just about this one instrument alone, but it is a remarkable piece of equipment. And it's remarkable we were able to build it, put it on orbit, and it worked first time every time. Next. Now, as you might have guessed, if anyone owns a telescope, just a curiosity, I can see most of you pretty much. How many people own a telescope right now? Put your hands up. Anybody? Okay. But a couple people. Good. You know how difficult it is sometimes to get the optics to line up. Well, this is What we have with our instruments is there's nothing when you have 18 segments that have to be put together. But with the actuators, we're able to know which mirror goes where the optic is focusing, and bring them all to one sharp focus. Next. First target, you see, this is taken in the infrared, and they just colorized it orange, red. You know, the star you're seeing over here, its brightness is about 10th magnitude, which is something on the order of about 40 times fainter than the human eye can possibly see. And it's overloading the equipment. You can see that burning. But look behind it. This is in the near infrared. These are all not stars. These are all galaxies. Some of which we never saw before. Next. So they did a check out for sharpness. Everybody probably knows and remembers that the Hubble Space Telescope went up. It was polished to the wrong prescription, and they had a problem with big problem with not being able to achieve a proper focus. Okay, I'm an optician. I partly take a little responsibility on that because the opticians that work with should have said there's something wrong here. Why aren't you testing this out like you're supposed to? Or they did. They said, "Yeah, it's fine. It worked perfectly." Yeah, that meant that they had to do their work. They did an incredible job on that. Several 3 spacewalks, new equipment put in to correct the undercorrected optics. We really don't get a second chance at all. So they really had to make absolutely certain everything worked. Luckily, they learned from that terrible event, and this instrument works fine. This is the sharpness check. The MIRI's fine guidance sensor to make sure the instrument is working, pointing, and staying on the guide. The near infrared cam and the near infrared spectrometer. These lines you're seeing over here. Those are slits that allow them to be using that instrument, each one of those 4 imagers, as a spectrograph, to be able to see and analyze composition, temperature, distance, a number of things. So everything worked out fine. Next. Okay, greater vision. This is a smaller instrument. It's a Spitzer infrared satellite. And same, this field of view, this is at about 8 microns, about as far as we can go with that technology. And yes, you see some stuff that's just on the border. It's always happens. Just on the border of detection. This is the Webb MIRI, 7.7 microns, a little bit shorter wavelength from that. Now you're seeing the same ones sharply in focus. Yeah, you get some scatter because you have all those mirrors together, but working together, we're able to see this. You see nebulosity gases and such that are lit up in the infrared so that you can see the heat energy is doing chemical reactions. Maybe you can go to the planets. Not a bad improvement. Yes. And this was first light. This is the first photograph. After all the testing was done, after all the alignment was done, that was taken. And what you're seeing over here, ladies and gentlemen, are objects most distant of which to here, more, down here. Yeah. These are out at about 10 billion light years. Almost not exactly to the brick wall, as they say, the edge of the universe. This is in one shot. All this. We are able to see all the crazy things happening here. This is a galaxy. This is another galaxy. And the light from this is being bent by this to make it into like a Watson shape. It's not a Watson, but it just took the image and twisted it from its own little galaxies over here, gravity. We're able to see. And then you have other objects all through, scattered through here. Some that look like our galaxy, some that just don't look like any type of object at all. This is the first light, as it's called. The first photograph, operational photograph. It's very important for all telescopes. Even if you build your own, it's incredibly important to you as the builder and to all the opticians that work on it, the engineers, everybody. Fantastic. Yes. Okay, so here we have an update. This is as of December. I just grabbed a few because I know this is a relatively long talk, and I appreciate your patience. Yeah. One of the first galaxies was imaged. I don't know the abbreviation, I'm sorry. MLM, maybe it's It's Z, it's Doppler shift 14. That's like out on the edge. 250 million years after the Big Bang. This is very old. It may not even exist anymore. If you had a super hyper warp drive and went out where it is, it may not be there anymore. It may have ceased to exist, burned out all its stars. We don't know. But it's the first time we were able to image it. Only a quarter billion years after the Big Bang, after the creation event. And here is a galaxy. Even getting this close to the screen, a large screen, it might even have some hydrogen gas around it. One tiny it's amazing. Next, there's an object, I believe it's in Aquarius, called the Helix Nebula. It's a planetary nebula. It's not a planet of gas. The original definition they thought of this maybe was a gaseous planet. Turns out it's just a round object. Usually, in this case, the Helix Nebula goes up in VISTA, which is a near infrared camera on Earth. They closed in on one section of it. This is the place where a star has died and stars being created from those ashes. Well, and this is a close up of Webb. You can see some of those objects with the cleared out an area around them where they form. This is remarkable. Yes. And then seeing protostars forming as we watch. They probably, if you ever travel out to them, you probably have a planetary system or at least a star sitting there. But you can see through the clouds of dust those stars coming in. The one thing I really don't like about the pictures that are coming back, because of the nature of the mirrors, they're all hexagonal, so they all have these 6 spikes going through them. But that's scattered light. There's not much you can do about it, but at least you're getting, Next. Okay, the last word. William Herschel, telescope maker in the 18th century. The inspiration of me. I was a kid. 10. And I read about him in a book called Pioneer Astronomers. David Sullivan wrote it was in Scholastic. If you get on a search area, I recommend searching a book search. You will be able to find a copy. It was a whole 50 cents. Amazing to a 10-year-old kid. It was so cheap. It's wonderful. I read about this gentleman. He could not, he could not afford to buy them, so he ended up learning how to make them. And in fact, one of those instruments was a 6 1/4 inch aperture, very similar to the 6-inch reflector telescope we have today. And he found what he thought might have been a comet, which was a little fuzzy with the thing. Over a period of a couple of nights, because really they didn't think very much of it. So okay, well, what's one more comet in the vastness of the universe? So he reported it though. And other people took it up, and as it approached the sun, it didn't develop a tail. It just went behind it and came back on the other side into the morning sky. Still this beautiful blue object. Suddenly they realized when they played with the numbers that it was on orbit around the sun, and it was the first planet ever discovered with the telescope. Not bad for a guy. Just drawing mirrors. Those mirrors were metal. They were pinky. Believe me, I polished enough metal to tell you. But William Herschel, of course, discovered the planet Uranus. And he also discovered infrared in an experiment where he had several kilometers and a prism blank from the sun in red and green and blue. And as it went further into the red, toward the red, the temperature kept going up. And then to calibrate it to the room to make sure his readings were correct, He moved along was by the red, away from it, and the temperature went further up. He had discovered the infrared. And that is what we use now to see the vistas of the universe around us. Next. Okay, I have to thank my wife Bonnie, who was patient enough to be able to help me get this together because I had problems trying to get the software to work. Mary Dugan allows me to give these talks. Thank you, Mary. NASA, of course, Canada Space Agency, European Space Agency, Northrop Grumman were the main contractors for it. But the optical work was done by Hall Aerospace. I tipped my hat to them. And L3 Harris was just the communications contract. What good is a space telescope, brain telescope, if you can't communicate with it and tell it what to view and how to view it? So all these people, incredible people. Well, thank you, and good evening.